Welcome back to Office Hours with Dr. Clark. So we are looking at share my screen here, my board. Okay, so we're gonna talk about stereochemistry today. Big topic in organic chemistry. So isomers, if you recall, we have, well, specific constitutional isomers. Constitutional isomers. Same molecular formula, different structural formula. Okay. So for example, butane compared to methylpropane. Same molecular formula, same C4H10, but there's different ways to represent that molecular formula. So these are two different molecules, right? They're not the same. We can also have constitutive isomers that are two different functional groups. This is C2H6. Oh, okay. So now stereoisomers, they have a different spatial arrangements, but same constitution. So the classic ones is the cis trans isomers, stereoisomers. So this is the stereoisomers of 2-butene. So we have the trans 2-butene, and then you have the cis 2-butene. Right. And they're both C4H8. So they're the same constitution. Double bond is in the same spot, but how they're spatially arranged is different, and you can't interconvert from one to another. Right? Right? So we call these are cis trans or geometric isomers. Okay. So there are different ways to look at stereoisomers. So for example, we can have what we call enantiomers, enantiomers. So let's take 2-chlorobutane. So 2-chlorobutane. These may look like the same molecule, but they're actually mirror images. So you can't superimpose one on the other. So non-superimposable mirror images. Right. So these are examples of enantiomers are non-superimposable mirror images. So we're gonna spend a lot of time with enantiomers actually. So another type of stereoisomers are called diastereomers. Diastereomers. These are stereoisomers that are not mirror images. I actually saw an example of that with the cis trans. So these are stereoisomers where they're not mirror images of each other. So an example of diastereomers is a cis trans stereoisomers. And we'll see some more examples. So we have to talk about chiral carbons. That's foundational to understanding enantiomers, diastereomers, some of these stereoisomers. So a carbon with, oh, I'm writing faster than my brain is processing, with 4 different attachments. So what we're saying here, let's look at my 2-chlorobutane again. So there are 3 hydrogens on this carbon. There are 2 on this one, and there are 3 on this one, and there's 1 on this one, and that's actually a dash. So this carbon is considered chiral because there's a methyl attached to it. There's an ethyl. So if you look at the whole picture, there's an ethyl, there's a methyl, there's a chlorine, there's a hydrogen. Right? So that's called a chiral carbon, also known as a chiral center, stereocenter. Now let's compare it to this molecule. There are no chiral carbons here because each carbon has at least 2 of the same thing attached. All right, so if we look at this carbon here, it has an ethyl group on one side, another ethyl group on the other side. So that is achiral. Right, so if a molecule has no chiral carbons, it is considered achiral. If it's chiral, then it can have stereoisomers. Let's look at a ring. The rings can be a little tricky. So let's say we have an OH here. Any chiral molecules on this ring. So it's okay, well, there's a hydrogen that's coming out. Yeah. So these carbons, this carbon, that one, none of those are chiral, right? Because they have 2 hydrogens, so that doesn't, that will count as not being chiral. But let's look at this one right here. It looks like it could be because an OH is an H, and then if I'm going around the ring, If I go on this side, I have a CH2, that's that CH2, keep going CH2. So no matter where I go on the ring, this side, the left side looks exactly like the right side. This is also a chiral. But what if, say, I had a ring scenario where I had two attachments to it, like an OH and another OH. H here, H here. Both these carbons are actually chiral. So let's see. So I have an OH, I have an H, and then I go on this side of the ring. It looks different from this other side of the ring, right? So this side compared to this side, they're two different sides, right? One has an OH, one doesn't. So that's chiral. And we can do the same thing with this carbon. This side, let's see, let me change my color. This side looks different than this side. Okay. All right, so there are two chiral carbons there. Two chiral carbons. Let's look at like how do we draw enantiomers? So there's a, so there's the, let's take this. This is a chiral carbon there. So we can have an enantiomer. So I could draw the mirror image, and that's the enantiomer. There's a pair of enantiomers. Now, there's a trick you can use. Let's take a different molecule. Let's take, let's say the bromine here. And I recognize that that's chiral, so I said, let me draw an enantiomer. There's a trick. All I have to do is change the orientation at that chiral carbon, and I get the enantiomer without having to figure out, okay, how do I draw the mirror image? Because when you have, say you have five chiral carbons, and it's a pretty complicated molecule, sometimes it's not easy just to flip it and draw a mirror image. But if you just change all the orientations at the chiral centers, you would get your enantiomers. Now, with one chiral carbon, you cannot get a diastereomer. But I'll show you an example where we can look at chiral diastereomers, right? So this molecule, both those carbons are chiral, and you can test it out. There are four different attachments to each carbon. I can draw the enantiomer very simply by just changing the orientations at the chiral centers. All right, so let's call this A, let's call this B. And I can make a diastereomer of A by keeping one of the chiral center the same and changing the other. Let's call these carbons 1 and 2, 1 and 2. Right. So A and B, no, I'm sorry, I'm not going to say equals. A and B enantiomers. A and C are diastereomers. So A and B are mirror images of each other. And you could actually turn B over and you can see how it reflects A in a mirror. And C is a diastereomer of A. It's also a diastereomer of B, right? B and C are also diastereomers. So in B and C and A and C are diastereomers. Okay. So something interesting about C is that there is a plane of symmetry. So there's a plane of symmetry. When I have a plane of symmetry between my chiral carbons, this molecule is considered achiral, or we call it a meso. These are chiral molecules. Right, so this is chiral, and this is chiral. The thing about chiral molecules, like specifically enantiomers, we can only distinguish enantiomers based on optical activity, which we're going to talk about in a second, as well as biological activity. For example, glucose has an enantiomer, and one enantiomer tastes sweet and we metabolize in our body. The other one does not taste good at all and we cannot metabolize it. So our body recognizes it. But if we were to take both of them in the lab, they would have the same solubility, same boiling point, same melting point, everything. So enantiomers are not easy to distinguish except for a couple properties. And one of them is called optical activity. Optical activity. With optical activity, basically, chiral molecules can rotate plane polarized light. So your enantiomers will rotate plane polarized light. So enantiomers will rotate it, that plane polarized light, in opposite directions. So either clockwise, we call that plus. Take this counterclockwise. So there's a plus glucose and there's a minus glucose, for example. And the plus we call D, there's a D glucose or L glucose. So there's actually numbers, like for example, you might have an enantiomer that rotates plus 42.6, and then it's well, one molecule that's chiral rotates 42.6 positive, and another one will rotate, the enantiomer rotate negative 42.6. Right? So they're equal but opposite rotations. So one is clockwise, one is counterclockwise. So that's how we can distinguish between enantiomers in the lab. Now in the body or in an organism, we can distinguish it based on, okay, this enantiomer, we know the D one is metabolized and the L one isn't. So we can distinguish them that way as well. Okay, so so there's a instrument called a polarimeter, and that measures optical activity. So we can look at molecules and judge whether they're optically active or not. So as we go here, this is chiral and optically active. Right, because there's a chiral carbon. There's one chiral carbon, so we can say that. We can look at this molecule and say it's achiral and optically inactive. Now here's a tricky one. We can look at this molecule and say, well, we have two chiral carbons, but since there's a plane of symmetry in the molecule, it is also achiral and optically inactive. All right, so this is meso. Another scenario that we haven't talked about yet is what if I have a 50-50 mixture, 50-50 mixture of enantiomers in a solution, right? Even though we have chiral carbons, the 50-50 combination is going to be also optically inactive. And we call that mixture a racemic mixture. So different scenarios. So you can have a racemic mixture, a 50-50 mixture. It has to be 50-50. It can't be 60-40 or 55-45. 50-50 mixture of enantiomers, you're going to have an optically active mixture. Your light will not rotate to the right or to the left. We have a compound that has a plane of symmetry, even though it has chiral carbons, it will also be considered achiral and optically inactive as a meso. Or we can have a compound with no chiral carbons. So no chiral carbons. That's considered achiral and also optically inactive. Or we have a compound with chiral carbons that doesn't have a plane of symmetry, and we consider that chiral and optically active. Okay? So these are different terms when we're talking about stereoisomers, enantiomers, diastereomers. We talk about cis and trans, and then we introduce optical activity. Now you can do some math with optical activity, which this video will not cover, where you can actually calculate what we call the specific rotation of your stereoisomer. But in a qualitative sense, we can say, okay, we can look at the molecule and judge whether we should expect optical activity or not. So in the next video, we're going to talk about how do we represent enantiomers in a formula, right? How can we say, okay, I want to draw this specific enantiomer versus this other one? How can we, communicate that? All right, but join us next time for Office Hours with Dr. Clark.